You know, folks, we talk a lot about tough jobs, and let me tell you, building in Nepal, that's up there. Imagine constructing on the side of a mountain with earthquakes always on your mind. That's where slab design comes in, the unsung hero of sturdy structures. Think of it as the foundation of your floors and ceilings, the backbone that holds everything together. Get the slab right, and you're one step closer to a safe and sound building. Mess it up, and well, let's just say you don't want to be around to see the consequences. In Nepal, it's not just about supporting weight, though that's important too. These slabs have to be tough enough to handle the tremors that shake this beautiful country. We're talking about designing for seismic activity, which adds a whole other layer of complexity to the job. And it's not just about making it strong, it's about making it flexible, able to move with the Earth's movements instead of crumbling under pressure. It's a delicate dance between strength and resilience, and it takes a skilled engineer to get it right. Now, when it comes to slab design in Nepal, there are a few things that make it a whole different ballgame. First off, you've got the terrain. We're talking steep slopes, rocky ground and limited access to heavy machinery. It's not like your typical construction site, that's for sure. Then there's the climate, from scorching summers to freezing winters, all of which can affect the materials and how they behave. But the biggest challenge of all, you guessed it, earthquakes. Nepal sits smack dab in the middle of a seismically active zone, which means those tremors are a fact of life. So, engineers here have to be extra careful, designing slabs that can withstand not just vertical loads, but also the horizontal forces generated by an earthquake. It's all about ensuring the building can sway and move with the shaking, instead of collapsing like a house of cards. Now, before you even think about pouring concrete or laying steel, you've got to do your homework. And by homework, I mean load calculations. This is where engineers figure out exactly how much weight each slab needs to support, both when the building's standing still, that's your dead load, and when it's full of people and furniture, that's your live load. They've got to account for everything. Walls, floors, roofs, even snow if you're up in the mountains. And here's where it gets really interesting. They use this thing called the Nepal National Building Code, the NBC. It's like the rule book for construction in Nepal, laying down the law on everything from materials to earthquake resistance. The NBC provides specific guidelines for calculating loads based on the building's location, height, and intended use. Think of it as a safety net, making sure engineers aren't cutting any corners when it comes to keeping people safe. All right, once you've crunched the numbers and know how much weight you're dealing with, it's time to pick your weapons, or, in this case, your materials. Now, when it comes to slabs in Nepal, two contenders reign supreme: reinforced concrete and steel. Concrete's the workhorse, strong and durable, especially when you add steel bars for extra muscle. It's great for resisting compression, that squeezing force, and it's relatively inexpensive, which is a big plus. Steel, on the other hand, is the high flyer. It's lighter than concrete and can handle a whole lot of tension, that pulling force. It's also great for spanning large distances, which comes in handy in those modern open-plan designs. Now, sometimes you'll see a combo of both concrete for its strength and steel for its flexibility, working together like a tag team to create a super strong slab. Section 5. Digital blueprints, modeling slabs with technology. Now, back in the day, engineers used to do all this stuff by hand calculations, drawings, the whole 9 yards. But these days, they've got a secret weapon: computers. Using software like ETABS or SAP 2000, they can create virtual models of the building and its slabs, testing them under different loads and conditions. It's like a digital dress rehearsal, allowing them to spot any weak points or potential problems before a single brick is laid. These programs are pretty amazing. They can simulate earthquakes, wind loads, you name it. They can even show how the slab will behave over time, taking into account things like creep and shrinkage. This level of detail helps engineers optimize the design, making sure it's not only strong and safe, but also efficient in terms of materials and cost. It's like having a crystal ball, but instead of predicting the future, it predicts the future strength of your building. Pretty cool, huh? Section 6. Stress test, analyzing slabs for strength and stability. Once the virtual model is built, it's time to put it through its paces. This is where structural analysis comes in, and it's all about understanding how the slab will behave under stress. Engineers look at things like bending moments, which is how much the slab will bend under load, and shear forces, which is how much it'll want to slide apart. They need to make sure the slab can handle these forces without cracking, breaking, or worse, collapsing. They use all sorts of fancy equations and principles to figure this out, stuff that would make your head spin, but trust me, it's important stuff. They're basically making sure the slab is strong enough to do its job, day in and day out, without any surprises. It's like giving the slab a stress test, but instead of a treadmill, it's getting hit with virtual loads and forces. Section 7. Teamwork makes the dream work. Collaboration in design. Now, here's the thing about slab design. It's not a one-man show. It takes a whole team of professionals working together, from the architects who dream up the building to the engineers who make sure it stands up, and finally the construction workers who bring it all to life. Communication is key here, folks. The architect needs to know what's structurally possible. The engineer needs to understand the design intent, and the contractor needs clear instructions on how to build it all. And it's not just a one-way street. There's a lot of back and forth, refining the design, making adjustments, and finding solutions that work for everyone. It's an iterative process, with everyone bringing their own expertise to the table. Because at the end of the day, it doesn't matter how beautiful the building is if it collapses on itself, right? It's all about finding that sweet spot where aesthetics meet functionality and safety. Section 8. From plans to reality, bringing slab designs to life. Now comes the really dirty part, the actual construction. The slab design might look great on paper, but it's up to the skilled workers on the ground to make it a reality. This is where precision is key, folks. Every measurement, every angle, every reinforcement bar has to be spot on. A small error here could have big consequences down the line. The process usually starts with building the formwork, which is like a mold for the concrete. Then comes the steel reinforcement, carefully placed and tied together. And finally, the concrete is poured, vibrated to remove air bubbles and left to cure. It's a carefully choreographed dance, with each step critical to the final strength and durability of the slab. Section 9. Standing strong, the importance of durable slab design. So, why go through all this trouble for a slab? Well, in a place like Nepal, where earthquakes are a constant threat, it all boils down to safety. A well-designed slab is the difference between a building that stands strong and one that crumbles under pressure. It's about protecting lives, livelihoods, and the cultural heritage that makes this country so special. But it's not just about surviving the next big one, it's also about ensuring that buildings last, providing safe and secure homes and workplaces for generations to come. A durable slab means fewer repairs, less maintenance, and ultimately a more sustainable built environment. It's about creating structures that can withstand the test of time, standing as symbols of resilience and human ingenuity in the face of nature's challenges. And that's a job worth doing right, wouldn't you say?